next speaker, Eng Poh Ng from University of Sains, Malaysia. Hierarchical mordenite zeolite prepared using salt and templating synthesis for cyclic acetals production via acetylation of glycerol and benzaldehyde.
Hierarchical modernization.
So, good afternoon, ladies and gentlemen. So today, I would like to present our work with the title of Hierarchical Modernite Zeolite prepared using soft templating synthesis for cyclic acetal production via acetylation of glycerol and benzaldehyde. So first of all, my name is Dr. Eng Poh Ng from School of Chemical Sciences, University of Science, Malaysia. So as an introduction, what are zeolites? So probably you might not know. So zeolites are crystalline porous material made up of aluminum silicate, and they have a defined micropores ranging from 0.3 to 2 nanometers. Usually zeolites, they have a high specific surface area in between 300 to 1,000 meters square per gram. And if we measure the total pore length of 1 gram of zeolite, you will have the distance of about 600 million kilometers, which is equivalent to 4 astronomical units. So you can see the distance between the sun and our Earth is equivalent to 1 astronomical unit. So it has 4 times longer than this distance. So zeolites are widely used in many applications because of several properties, such as a tunable chemical composition. They are chemically and thermally stable, and eventually they are also mechanically stable. And zeolites, they are eco-friendly, and most importantly, they are recoverable and reusable. As a result, zeolite has been used as a catalyst, gas, and molecular separation ion exchange processes. So far, there are more than 250 types of zeolite have been identified by IUPAC, and one of these zeolites is called mordenite. So this mordenite zeolite, it is very useful because of the high silicon over aluminum ratio, and they have a very large pore opening. Then this large pore opening, it can enable the molecule to pass through and to react inside the zeolite pore. In addition, this zeolite is more thermally stable, and it is resistant to acid corrosion if compared with other zeolite. However, the pore size of a mordenite zeolite is still not big enough when we apply the reaction involving bulky molecules. So, in order to solve this pore accessibility issue, cooking and deactivation problem, several methods have been developed in order to increase the pore size of the zeolite. We call it as a hierarchical zeolite, where the zeolite will have a micropore, and also they will have a larger pore size, which is called mesopore. So the first method is called if you see from here, these three zeolite have a similar XRD pattern like the theoretical one, so it means that they are pure mordenite zeolite. In addition, we also can see that the TM0.2 and TM0.3, they have a lower peak intensity as compared to the parent mordenite zeolite. So it means that they have a lower crystallinity. And also, these two samples, they shows a peak broadening. Okay, so it means that they have a smaller crystal size. On the other hand, for the TM0.4, it shows a totally different XRD pattern compared to these three samples. So after we identified, it has this ANA and gismondine interboron dense phase. So that means this is not a pure mordenite zeolite. So based on the XRD data, we can say that the maximum OTMS over alumina ratio is 0.3. So beyond 0.3, then you will form other crystalline phase. Okay. Next will be the infrared spectroscopy, and we can see for the mordenite zeolite, TM0.2 and TM0.3, so they have a similar IR pattern here, and these few IR bands here corresponds to the composite building units. For example, 781, 733, 688, 631, it corresponds to these four types of composite building units. So these three samples, we can see we can have these signals. However, for the TM0.4, which is not mordenite zeolite, it shows a totally different IR pattern as compared to these three samples. So that means this agrees with the XRD analysis. However, for the TM0.2, TM0.3, and TM0.4, it shows extra peaks here relative to the pure mordenite zeolite. So this confirms the presence of OTMS incorporated into the framework of the zeolite. For the scanning electron microscopy, we can see from these four samples that the parent mordenite zeolite exhibit elongated orthorhombic shape, whereas for the TM0.2, it shows a rectangular bar-like shape. And if we further increase the OTMS to 0.3, it will give us a nano needle shape. And if we further increase to 0.4, and it will form an aggregated flower-like shape. So we can see that overall, the mordenite zeolite shows like a stick shape, whereas for the TM0.4, which is not mordenite zeolite, it shows a different morphology. Furthermore, if we introduce this OTMS into the sample, and we also observe the increase of silicon over aluminum ratio from 6.14 to 6.70, 6.79, and 7.07. So that means once we increase this ratio, it can give indirect hints about the enhancement of the surface acidity. In addition, we also use thermal gravimetry and differential thermal gravimetry to study these four samples. And for the parent mordenite zeolite, it shows weight loss at about 105 degrees Celsius, and also 255 degrees Celsius based on the DTG analysis. And if we incorporate the OTMS, and we can see the additional weight loss at 280. So you can see here, once we introduce a OTMS, then we can have the additional signal here. This is due to the incorporation of OTMS. So based on the calculation, we can observe that the OTMS are incorporated into TM 0.2, 0.3, 0.4 is about 17 to 21 millimole of OTMS over 1 gram of zeolite solid. In addition, for the TM 0.4, which is not a mordenite zeolite, it shows a narrower DTG signal at 100 degrees Celsius. This is due to the hydrophobic surface and also the smaller pore size of this ANA and gismondine intergroup. We use nitrogen adsorption to study the porosity, and we can see for the parent mordenite zeolite, it shows a typical type 1 isotherm. So that means it is a truly microporous material. And if we introduce OTMS with 0.2 and 0.3 molar ratio, it also shows a type 1 adsorption isotherm, but with additional hysteresis loop at relative pressure of 0.45. So this hysteresis loop indicates the presence of the mesoporosity. So that means these two samples, it has micropores and also mesopores. And for the TM 0.4, interestingly, it shows a type 3 adsorption isotherm, and it shows that this TM 0.4 has no pores in the sample. So it means it is a non-porous material. The nitrogen adsorption is further derived in order to obtain several parameters like specific surface area, micropore surface area, external surface area, mesoporous volume, pore volume, total pore volume, and also average pore size. We can see for the pure mordenite zeolite, it has these values, okay? And if we introduce OTMS, TM 0.2, 0.3, the surface area reduces, and also for the micropore surface area also the same. However, the external surface area increases from 13 to 34 and 46, and mesopore pore volume also increases from 0.09 to 0.14, 0.17, and for the average pore size is also increases from 5.1 to 6.8 and 8.3. So this is a good sign, indicates that we have the mesopores inside these two samples. In addition, when we increase the OTMS ratio, the surface acidity is reduced. Okay, total acidity is reduced, but the acid strength increases from 1.1 to 1.2 to 1.3. For the TM 0.4, we can see it shows a very low PET surface area and surface acidity. So this is due to the non-porous structure. Next, we will see the catalytic performance of these four samples in acetylation of benzaldehyde with glycerol. So we conduct it using a 0.05 gram of a catalyst with a benzaldehyde glycerol ratio 7 to 1, and the temperature is 140 degrees Celsius for 60 minutes. So if we did this reaction without catalyst, the conversion is only 22.3. So if we introduce the pure parent mordenite zeolite, so the conversion increases significantly to 67%. Then if we introduce TM 0.2 and 0.3, we can see also an increment in the reaction conversion. So that means the introduction of hierarchical mesoporosity is beneficial for the catalytic reaction. So among these these three samples, hierarchical TM0.3 is the most active catalyst, and it gives a conversion of about 84.3% after 60 minutes. On the other hand, for the TM0.4, so this is non-mordenite zeolite, and it gives a conversion of about 52%. So for the selectivity of the dioxolate, we can see without catalyst, the selectivity is around 50%, and for the mordenite and hierarchical mordenite zeolite, the selectivity increases from 50% to about 65%. So it means that the presence of the mordenite zeolite is good for the selectivity of a dioxolate product. For the catalyst loading, since TM0.3 is the best catalyst, so we will study this parameter by using TM0.3 catalyst from 0 until 0.2 gram. And the temperature will be 160 degrees Celsius. Time is 20 minutes. Without catalyst, the conversion is around 26.2%, and we can see it increased very significantly to about 88.6%. So this is due to the increased number of acid sites when we introduce a more catalyst amount. But when we further increase the catalyst amount to 0.5 and 0.2, we can see the conversion start to goes down. So this is due to the excessive catalyst amount in the sample, in the reaction liquid, and it causes inefficient stirring. Nevertheless, for the selectivity of dioxolate, it is still maintained even though we increase the catalyst amount. So you can see these blue bars, conversion is still the same. We also performed the catalyst comparative study for this reaction, where we use homogeneous catalyst and other zeolite catalyst for comparison. Basically, for the strong homogeneous catalyst like hydrochloric acid and sulfuric acid, concentrated sulfuric acid, they give 100% of glycerol conversion, but the selectivity towards dioxolate and dioxane very low. So you can see the conversion is only, the selectivity is only 6.7 and 4.7% for these two compounds, and HCl is only 54 and 30% for these two compounds. However, for the acetic acid, although it gives a low conversion, 37.6%, but it gives a better dioxolate and dioxane selectivity. So the low conversion is due to the weak acidity. On the other hand, for the protonated zeolite such as HY, HLTL, and basic zeolite such as NaX and NaA zeolite, the activity or the conversion is quite low compared to TM0.3. So this can be explained by their weaker acidity and basicity, but the dioxolate selectivity is almost same like TM0.3. So among all these catalysts, we can see that hierarchical microporous, mesoporous TM0.3, it shows the best conversion, and this is a turnover frequency. You can see it shows very high, which is higher than the others catalysts here. So the high activity can be explained by its surface acidity and also hierarchical mesoporosity. And we also did the reusability of the catalyst. Since these homogeneous acid catalysts, they are not recyclable. So once we use it, then we cannot recover back. But for the this TM0.3, we can use up to 5 cycles with just slightly drop in the conversion, but the selectivity is still almost maintained. As a conclusion, amorphous silica from bamboo leaf has been used to synthesize mordenite zeolite, where the OTMS is used as a mesoporogen. The optimum OTMS over alumina ratio for synthesizing hierarchical mordenite zeolite is 0.3. So we label this sample as a TM0.4. So this the resulting hierarchical mordenite exhibits nano-needle morphology. So this is a TM0.3, and it has reduced acid density, but with increased external surface area, mesopore volume, average pore size, and acid strength. So among all the samples that we prepared, TM0.3 is the most active in acetylation of benzaldehyde with glycerol. It gives 54.1% conversion and 61.5% selective to dioxolate, which is better than other zeolite catalysts and also homogeneous catalysts. Lastly, the TM0.3, it shows a high reusability with minimal loss in activity after 5 cycles of reaction, and it offers it as a potential acid catalyst for chemical production when it's involved with the bulky molecules. So for the acknowledgement, I would like to thank Fundamental Research Grant Scheme and University of Science Malaysia short-term grant for making this project successful. And that's all for my presentation.